Now our buddy Kirchhoff did a whole bunch of work with electric circuits, and so he came up with the second law that has to do with voltage. So our first law was Kirchhoff's current law, which says the sum of the currents that enter a junction have to be equal to the sum of the currents that leave the junction. Kirchhoff's voltage law is now basic conservation of energy. So it states that as charges flow around the circuit, they experience voltage gains in the cell and voltage drops across the resistors. For every path through the circuit, no matter which direction you choose to go, the voltage gains have to equal the voltage losses. So the sum of the voltage gains has to equal the sum of the voltage losses, no matter which path around the circle you take. So in terms of your ski hill analogy, if you get 6 volts as you go through the battery or go up the hill, say you go up 6 meters, then no matter what path you take, when you get to the bottom, you need to lose 4 volts and 2 volts. That's going to give you 6 volts. Or this would be like saying you lose 6 meters and 2 meters to get back to the bottom of the hill. You have to lose as much as you gain in terms of voltage and in terms of height. So let's see how this works out. Example number 4. Find the unknown voltages and voltage drops. So we start with the battery that says I'm going to gain, my voltage gain is going to be 20 volts. So all the electrons or all the current leaving this side of the battery, flowing upwards, has 20 volts. You could think 20 volts of energy. It's gained 20 volts of electric potential. And then as it comes along, if it hasn't gone through any resistors yet, it's still going to have 20 volts. Now, the first resistor it goes through takes away 8 volts. So 20 volts takes away 8 volts. It only has, at this point, your electrons only have 12 volts of energy. That's 20 minus 8. Then, as you're going along, doesn't tell us here how much the drop is, doesn't tell us here how much the voltage is, but it tells us over here the voltage is 0. So in order to get all the way back to the battery, we have to lose as much as we started with. So we've already lost 8. So this must be a voltage drop of 12 in order to get us to a voltage of 0 by the time we get back around. So that we gained 20 at the beginning, and we lost 20, 8 plus 12, as we went around our circuit. And that's going to be true no matter which loop you take. So, for example, in this case, I have a 10 volt gain. So I have 10 volts to start with. And unlike current, these 10 volts don't distribute themselves along the circuit. Each electron, you could say, has 10 volts of energy. So they take those 10 volts of energy with them on both paths. So this is going to be 10 volts because I haven't gone through any resistors yet. And this is also going to be 10 volts because I haven't gone through any resistors yet. So what that means is these 10 volts, if I'm going to get back to the battery, I have to lose them in this one path. My electrons get to go along and choose one direction to get back to the battery, or they could go along and choose the other direction to go back to the battery, but they're not going to go through both ones at once. So in either case, in order to get back to the battery, having lost as much as we started with, we need a voltage drop of 10 volts to get us to 0 volts in order to get back to the battery, so that no matter what path I take, the amount I gained at the battery is the amount I lost in the path that I chose. This is going to have some pretty cool implications as we go along. So, for example, find the unknown voltages and voltage drops. So 12 volt gain in the battery means we're going to have 12 volts here coming along the circuit. 8 volt drop. Well, if I lose 8, I had 12, I lose 8, that means by this point I've only got 4 volts left. And those 4 volts are going to go both directions. So these electrons take 4 volts with them. These electrons have 4 volts of energy with them. Let's make those 2 to 3 sig figs. No matter which direction we go, and that means we must lose the rest of that in order to get back to the battery. So I got a 4.0 voltage drop to give me 0 volts then by the time I get back, and in both cases. So the implication of this is that parallel pathways, when I have a choice, will have the same amount of voltage drop on both paths. So that no matter which way I go, I lose this 8 because I have to go through this resistor no matter which path I choose later on. But in both of these paths, I have to lose the remaining 4 in order to get back to the battery and equal the voltage gain. All right, here comes another one. 60 volt gain, so at this point I've still got 60 volts. I lose 15 of them, so 60 minus 15 is only 45, so I've got 45 as I choose each of these paths, no matter which path I go along. Then it tells me I've got an 18 volt drop here, so 45 minus 18 is going to be 27 volts left after I go through this resistor. 45 minus 27. And that means as I keep going along, I've got to get rid of the rest of these 27. So this is going to be still 27. And I've got to lose the rest of that in this last resistor in order to end up with 0 when I get back to the battery. So started with 60. When I chose, I got 50. I lost 15 no matter what. So I had 45 left to come this way. Minus 18 left me with 27. And then the rest of those 27 have to be lost here. But again, no matter what pathway I take, I have to lose all my voltage. So 60 volts minus 15 left me with 45 here. Came down this way, 45, this would have left me with 35 volts because I lost 10 more. And I know I'm going to lose 27 more by the time I get to this path. So in order for this to work, 35 minus 27 means I have to lose 8 volts here in order to make this work. Or in other words, I have to exit this loop as well with only 27 volts to work with. So again, whichever path I take, I have to lose the same amount. So an 18 volt drop here is equal to the 10 volt drop and the 8 volt drop in these two resistors on the parallel path. So no matter which pathway I choose, I'm going to lose all my voltage by the time I get back to the battery. Note that there are two really useful conclusions to draw from Kirchhoff's voltage law. For any complete loop around the circuit, the voltage drops equal the voltage gain. Well, that's what it says right off the bat. And then no matter what way you go between 2 points, the drop must be the same. So between this point and this point, I've got two choices. I can go 18 volt drop on this resistor, or I can go 10 plus 8 on the other resistor to get to the same place. So this is actually just the circuit that we dealt with before. So we got one complete loop going this way, second complete loop coming around, and you have to end up with 60 volts no matter which way you go. To see the voltage analogy relationship, it's sometimes helpful at first to redraw the circuits so that the resistors are pointing quote-unquote downhill. So you think more like a skier. So for instance, consider the previous circuit, 5A, which they've redrawn here for you. This circuit can be redrawn in the following manner. So you can see that the cell acts like the chairlift leading to the top of the mountain. And then once at the top, all the skiers must descend by path R1. They don't have a choice. They're all going to go through this resistor. So they put that resistor here. This is resistor 1. Everybody's got to go through down that part of the hill. Then they have a choice, which they've drawn as like a splitting. And it says skiers then have a choice of path R2 or R3, both of which end at the bottom of the hill. So we can go R2 or through R3, but either way, we have to be able to get back to the negative end of the battery, which is like the downhill end of everything. 5B, on the other hand, can be redrawn as follows. So we've got here, again, the cell is like your chairlift going up the mountain. Everybody has to go through resistor 1, the 15 voltage drop. But then you've got choice of which way you want to go. You can either take the 1 resistor path, that's the 18 volt drop, or 10 volts and 8 volts. That's the other option. But either way, you have to get to the same point on the hill when you get back to the other junction. And then you have a little bit more of the hill left to do as you finish your loop to get to the bottom of the hill. Example number 6. Write equations relating the voltage drops VT, V1, V2, V3, V4, and V5 in the above circuit. So we're looking at this still, and we need to figure out what relationships or how to relate these different voltages. So we can start by thinking about the complete paths that we can take. So if we say VT is equal to, so this voltage gain that we get going up the hill would be equal to V1 plus V2 plus V5 to get us back to the bottom of the hill. That's one option. V1, V2, V5. So this is equal to V1 plus V2 plus V5. So that's one relationship relating the voltages. The other relationship would be the other pathway. So this would be, okay, we gain all that coming up the hill, VT, and then we can go V1, V3, V4, V5. So V1, V3, V4, and V5. And then we've got one more relationship that you, if you like, you could write down, and that is that on the two paths, these also must equal each other. So V2 has to equal, so the voltage drop here has to equal V3 and V4. So that's how we would relate all of these together. We don't usually write it out in symbolic form. We tend to just work with the numbers directly, but this is how it would look. All right, take some time to think about that, and then good luck on your homework.